The double-slit experiment is one of the clearest and most mysterious demonstrations of the quantum world. Imagine a simple setup: a barrier with two narrow slits, a screen behind it, and a source of light or particles in front. If you shine ordinary classical light or toss tiny pellets through the slits, you might expect each slit to act like a separate doorway. Particles go through one slit or the other, and the pattern on the screen would simply be the sum of two single slit shadows. That is exactly what happens with classical bullets or with water droplets. The pattern is additive and predictable. But when light or microscopic particles such as electrons are sent through the slits, the result is startling. Instead of two simple bands on the screen, an interference pattern appears. A series of bright and dark bands, as if waves from the two slits had overlapped and interfered with each other. The bright bands are where the crests of the waves reinforce each other. The dark bands are where crests meet troughs and cancel out. This interference is the unmistakable signature of waves. The mystery deepens when we make the experiment more delicate. If we turn down the source so that only one particle at a time travels toward the slits, and we record each arrival on the screen, those single impacts gradually build up the same interference pattern over many trials. Each click on the detector looks like a particle arriving at a definite point, yet the collective distribution of many such clicks matches the pattern produced by overlapping waves. In other words, each particle behaves like a wave spreading out and interfering with itself. But it is always detected as a localized particle. This dual behavior, wave-like propagation and particle-like detection, is what physicists call wave-particle duality. To make matters even more puzzling, if we attempt to determine which slit the particle actually passed through, the interference pattern disappears. Place a detector at the slits to measure the particle's path, and the screen shows two simple bands, as if the wave behavior were destroyed and the particle chose a definite slit. The mere act of acquiring which way information changes the outcome. Physicists interpret this as a fundamental feature of quantum systems. When you force the system to reveal a particle-like property, the wave-like possibility that produced interference is suppressed. This is sometimes summarized as the principle of complementarity. Certain properties, like path information and interference visibility, cannot be fully exhibited at the same time. Underneath these observations sits the quantum formalism. A particle is described by a wave function, a mathematical object that assigns an amplitude and phase to every possible location. The wave function evolves like a wave and can pass through both slits simultaneously as a superposition of alternatives. The probability of detecting the particle at a particular point on the screen is given by the square of the wave function S amplitude there. Interference arises because the amplitudes coming from each slit add together and then are squared, producing regions of high and low detection probability. When a measurement is made to determine which slit the particle went through, the superposition is effectively destroyed. The wave function collapses into one of the alternatives, and the interference terms vanish. Different interpretations of quantum mechanics offer different pictures of what is really happening. The Copenhagen interpretation treats the wave function as a tool for predicting probabilities and accepts collapse. As part of the measurement process, the many worlds interpretation avoids collapse by positing that each possible outcome becomes real in a branching world, such that both slit path possibilities coexist in separate branches and interference is absent once branches decay. Pilot wave theories, like Bohmian mechanics, keep particles on definite paths guided by a real pilot wave that produces the interference effect. Whatever the interpretation, the experimental facts remain the same and are reproduced by the same quantum equations. Modern experiments have explored the double-slit setup in ever more refined ways, using electrons, atoms, molecules, and even large organic compounds, detecting entanglement between particles and which-way detectors, and demonstrating how environmental interactions, a process called turn quantum superpositions into classical mixtures, explaining why macroscopic objects don't normally exhibit interference. The core lesson of all these tests is both simple and profound. At the quantum scale, reality resists the neat categories of wave or particle. The behavior you observe depends on the experimental context and what you choose to measure. Wave-particle duality is therefore not a failure of our instruments, but a clue that the quantum world obeys rules that differ from everyday intuition. In closing, The double-slit experiment forces us to accept that quantum objects are described by probabilities and possibilities, and that these possibilities interfere like waves until an act of measurement yields a definite, particle-like result. It is this blend of spread-out possibility and point-like actuality that makes quantum mechanics so strange, so precise, and so powerful, a core mystery that continues to shape physics and the way we think about what it means to observe the universe.